So hello everyone, this is lecture 4 for the error analysis. We completed 3 lectures. In the last lecture, we studied about the error propagation formula and we saw some examples, solved the examples, and we made it very clear that we understand the error propagation very well. Now, in this fourth lecture, just study what we already studied in our elementary classes, that is the mean and standard deviation. So why we use these in our calculations? So there is just one example to understand that how to calculate standard deviation and mean. So if these five observations are given, the 71, 72, 73, the units are omitted because of convenience. Given 5 measured value, what should be our best estimate value for x? So, what should be the best estimated value? So, we all know that reasonably our best estimate value would be average of mean x of 5 values, that is 71.8. Now, we can measure the variation, that is the deviation. Then we made this table, and this deviation we calculated, then we squared it here. We squared and we made this table. Okay, this square part is called residual also. Now if we take the average of the deviations only, then we will get this. First of all, to calculate the deviation, then we should take the mode, or we can just add up as it is, and then divide it by the number of observations, that is 5, and we will get 0 in the deviation. Why? Because there is this variation in the negative part and the positive part from the mean value. That's why we are getting something like 0 or close to 0. But if we calculate the average of residual part, this part, then we will not get 0. Then we will not get 0. That's why average of the deviations is not a useful way to characterize the reliability of the measurement x1, x2, xn, because this we get 0 here and still there is deviation, so we didn't get anything solid. So the best way to avoid this is to square all the deviations, which will give a set of positive numbers, and then average these numbers to obtain sigma di square. So now we take the square root of the result we obtain, and we'll get the result which is in the same units as x. Okay, so it is just we get calculate the sum of all squares and divide by n. Then we take the under root. Then the quantity we get is called the standard deviation. Okay, standard deviation or root mean square deviation of the measurement x1, x2, xn. So from the previous observations, we found that sigma x is equal to 0.7. So now we are getting something. Now we are getting something as compared to deviations where we get the 0. So that's why the importance of this is more. We will understand it how it is in just wait for a second. So there is this formula. Standard deviation has alternative derivation. There are theoretical arguments for replacing n by n minus 1. Means in the physics, when we calculate these observations and we take the all the record and we plotted it, then we find that if we divide the sum divide by the n minus 1, if n is the number of observation and divide it by n minus 1, then we will get more accurate result theoretically. That's why we're gonna use this formula wherever in the exam, in the net exam or any exam, it will be asked to calculate the standard deviation in physics. Then you will use this formula, divide by n minus 1. Okay, so just remember this. The standard deviation of the following data set. So there is this example and we need to calculate the standard deviation. So how will you do? You just made a table, you calculate the mean value, then you subtract it from the original values, then you squared it, then again sum, and then divide it by n, not n, just divide it by n minus 1, then you will get this standard deviation 0.07. So this will be standard deviation. Now the physical significance. I hope it is clear. Just try to focus because this PDF is blurred actually. So I'm dictating standard deviation as the uncertainty in a single measurement. So what does this mean, the standard deviation? As we learned, the standard deviation sigma x characterizes the average uncertainty of measurements x1, x2, xn from which it was calculated. So it is nothing but the deviation from the measurements. If we measure the same quantity n times, if we measure something which is we are measuring n times, always using the same method, and if all sources of uncertainty are small and random, then our result will be distributed around the true value. Okay, I hope you understand this. That if we are measuring something, then definitely we will get different results. Means not that different, means they are something nearby true value, but all the time you will gonna get different results for the same quantity. That's why we calculate error actually. So our result will be distributed around the true value x true in accordance with S called bell-shaped curve. So we will get a bell-shaped curve. So bell-shaped curve is like this. This is like this. Let me do it again. It's like this. Straight line. This is this. This is this. So if we calculate the observations, so in the y-axis we have uh, the value, okay, and on the x-axis, sorry, on the x-axis we have value, and on the y-axis we have number of particles. So number of particles are decreasing with and we have this x naught here, mean is here. So we are going in this direction. Then we will see that number of particles are decreasing or observations are decreasing with the very far result from the true value, and here also it is decreasing. So it's a bell shaped result we get here. Okay, so that more values will be, largest number of values will be nearby true value here. So this graph we get is bell shaped curve. Let me move it. So where were we are here. In particular, so what does this mean, this curve? In particular, 68% of your result will fall within a distance sigma x on either side of the true value. So on the graph, the 68% will be under this sigma x value. So the probability will be also 68%, will fall in the range of x true plus minus sigma x. That's why we calculate the sigma x, means most of the observations fall under the sigma x. That's why we get a very good result or the very good error. In other words, if you make a single measurement using some method, the probability is 68% that your result will be within sigma x of the correct value. So if it is asked in the question that what will the probability if you are using the standard deviation, then it will be 68% that you are measuring the value will come under x true plus minus sigma x. Okay, I hope you get it. We can take sigma x to mean exactly what we have been calling of uncertainty. That is, if we take one measurement of x, the uncertainty associated with this measurement can be taken as delta x or sigma x, as we studied in the error propagation formula. So there is this new term, that is weighted average. So what is this? It's nothing but it's like there are two people who are measuring, means just like I am in at the north pole and there's some other person at south pole. At the north pole I take the 100 observations, and at the south pole he take 200 observations for the same quantity. Then we gonna combine our results. Then how are we gonna combine our results to get some particular value? So it's about that we have some weight in our values. So how we calculate it? When a physical quantity is measured at separate locations and questions arises how these measurements can be combined to give best estimate, let two students A and B measure quantity X and obtain the following results. So student A get XA plus minus sigma A. Student B get X equal to XB plus minus sigma B. Each result will probably be the result of several measurements when X equal to mean of all A's and sigma A is SD of that mean, that is standard deviation, and XB mean of all B's measurements and SD of that mean. The best estimate for X is obtained as follows. So what is the weight? Weight of A value will be 1 upon sigma A square. Just remember this formula. Weight of B will be 1 upon sigma B square. And we when we need to calculate the X average, that will be omega A XA plus omega B XB divided by omega A plus omega B. So it's not just for two values. If there are n peoples at n different locations and you need to measure, then it just series will go on Likewise, it is given omega A xa, omega b xb, then omega c xc, and omega d xd, and bottom the all sigma omega. Okay, and if you need to calculate the uncertainty in the average uncertainty, if you need to calculate, then that will be 1 upon root sigma omega. Okay, of all the observations, you will see in the example. Okay, so here is this example. Workers from two laboratories report the lifetime of a certain particle as this and this, both in nanoseconds. If they decide to combine the two results, what will be their weight and their weighted average? So weight will be the sigma 1 is given, sigma 2 is given, 0.5 and 1. So we just use the formula 1 upon sigma a square, sigma b square. We will get the weights, and we calculate the x average value using the formula. And if we need to average in the value, that will be 1 upon root sigma or sigma omega I. That is summation. Okay, so there is this one more question. Each of these students measures the same resistance several times, and their three final answers are these. Now we need to combine them, so we get 113 as omega 1, omega 2, omega 3. We get the calculate the weight. That is the weight actually. Then we will get the R average. That is why the formula we used, and then the sigma average. There is one more question. Find the best estimate and its uncertainty based on the following four measurements of a certain voltage. So it is 1.4 plus minus 0.5, 1.2 plus minus 0.2, 1.0 plus minus 0.25, 1.3 plus minus 0.2. So we get the errors, and that's why we can calculate the weight. That is 1 upon sigma 1 square, sigma 2 square, sigma 3 square, sigma 4 square. And then we use the formula, we get the value, and again we can calculate the sigma average also. We can write the net V. This is one more question. All are on the same formulas, the same background. Three groups of particles. Physicists measure the mass of a certain elementary particle with the results. These are the three values are measured by three scientists or three physicists. Find the weightage average and its uncertainty. So we can calculate the weight. Then we can calculate the average values. The same formula. Okay, there is one more question. The speed of sound is given by these. Find the best estimate for u and its uncertainty. So same, you will use the same. There is one more question. A student performs an experiment to determine the voltage of a standard cell. The student makes 40 measurements with the apparatus and finds the result this, with a spread S1 equal to, this spread is nothing but the sigma or the variation, or we call it standard deviation. In the observations, after looking over for data, she realizes that she could improve the equipment to decrease the uncertainty by a factor 2.5, that is S2 equal to 0.004. So she makes two more observation that yields x2 average equal to this. Find the best estimate value. So in the question we find that it doesn't matter how much observations you take, it's results that that person got this result 1.022 plus minus 0.01, and when he improves that, then that will be called the second value, that is 1.012, and with error 0.004. Now we need to combine these results, so we use the same formula. Okay, so here it ended the weightage or weighting errors. Now we have something, that is how to measure pressure in gases. How do we measure the pressure? So first of all, you need to understand the pressure. So we measure the temperature, pressure in various units. That is atmospheric pressure and torr, or we also measure in mercury. That is in centimeters. That is for the manometer actually. So here we are given the range of the pressure in torr. So what is torr? Torr is nothing but 133 Pascal. That is 1 atm equal to 10 to the power 5 Pascal. So you understand what I'm talking about. 1 Pascal is nothing but Newton per meter square. 1 maybe. Just check. Okay, so what type of instruments we have to measure the pressure? If we need to measure the pressure between the range of 760 to 1 torr. Torr came from the Torricelli. Torricelli was a physicist who just measured the pressure by manometer. Okay, so you studied about him in the 11th class. If you studied there, then that's from where torque came. So if you need to measure the 760 to 1 torr range pressure, then that will be measured by mechanical gauges that are manometer, barometer. We have many, and if we see this, it is Borden gauge diaphragm, the name of the gauge which we use to measure. Then if we need to measure a small pressure, that is 1 to 10 to the minus 3 torr, that will be measured by thermal conductivity. And there is one name of this gauge, that is Pirani gauge. You can search about it. Then, if very small pressure you need to measure, that 10 to the minus 3 to 10 to the minus 13 torr, or this is like a vacuum case. Not exactly vacuum, but it is very small pressure. So you will use the ionization of gases experiments. So the name of that instrument uses panning gauge. We use to measure this pressure. So there are some more. We have gauges name. That is, if you need to find the 10 to the 3 to 10 to the minus 1 torr, then YouTube type structure is there. 1 to 10 to the minus 3, then thermistor, thermocouple. 10 to the minus 2 to 10 to the minus 5 torr, then Pirani gauge will be used. And if it is very small, then 10 to the minus 6 torr, then you will use panning gauge. And you can use for all negative values of 10 to the minus to 10 to the minus 11, that hot filament ionization gauge. And there is one more cold cathode gauge for all the small pressures. Now here is one we will study, that is hot cathode ionization gauge. So how it works, so we'll get a better understanding how we measure pressure in actual instruments. So it is not that much hard. We have this formula. This is nothing but, this is not T, it is I positive is equal to Si. That is not delta, it's S, Si negative P. So here S is sensitivity of the gauge. It is different for different gases or different gauges. I negative is negative current, that is E current. I positive is ion current, and P is pressure. So still you don't get the idea, I know. Let me show you this structure first. See this, it is ionization gauge. Here you are seeing this is vacuum chamber. So this is nothing but to maintain the vacuum. Here we put some pumps which just take the air out, pump out the air from here out, then it will maintain the vacuum here. That's how we put the gases which you need to measure the pressure of. Here we put the gases. Okay, so these are the, let's say, gas ions, or they are the molecules yet, not ions yet. Okay, so now what we will do, we will this is tungsten or any electron gun we can use. Okay, so from here, this is all the circuit you can see. It is positive side, it is negative side, and we need to find the pressure of the gas inside the this chamber. This dotted I represent. So when we start giving some voltage from here, then we see that electrons will flow in this direction. They will flow in this direction, and they will, because of heating of this tungsten here, the electrons will emit it, and because of this connection here, it will give positive this side. So that's how we will get electron in this direction. And when electrons collided with these molecules inside the chamber, they will ionize the molecules. And ionize, then those positive ions will move in this direction. So it will give us the I positive current. Because of this negative potential, we will get the current in this direction, and the electron current will be in, electrons will moving in this direction, and current will be in this direction. Okay, so we can see from this circuit that more the amount of I positive current we get, means more the pressure of gas inside. How? Because if there is large number of particles, and it is they are striking with high pressure, then they will be more ionized, and more ionized will give more I positive current. Okay, so that's why we can write this equation: I positive current is directly proportional to pressure, and we get this I negative current. More the I negative current, it depends on both. If more the I negative current, more the I positive current, and more the pressure, more the I positive current. Okay, this S is the sensitivity of the gauge. So I hope you get this relation how we calculated this. So now there is can be one example I give you. A question can be made like sensitivity given in millibar inverse S equal to 10 is given, and we need to find the pressure, and this is also given I positive by I negative. So what will be used? We use just simple this formula that will give us P equal to I positive by I negative multiply 1 by S. So it will be 1 by 10, 1 by 10 multiply 10 to the minus 1, and that will be in millibar inverse. So it will give us, if we convert it in bar, then what we will get, this will come in denominator, and millibar then will give us 10 to the minus 3, 10 to the minus 3 bar. Okay, that will come on the upside, and we will get 10 cube minus 2 we will get here, and it will cancel out, and it will give us pressure equal to 10 power minus 2 millibar. You just calculate it using the units, you will get the same result. This 10 power minus 2 millibar using the this formula. Let's use this formula, you will get this result. Now if we want to plot the V and the I positive, what's V here? V is this potential, this one. This one is V. So more the V, more the V, or we can say, or it can be here also. Then if, well, that's how the potential is increasing, then we are getting that I positive current is increasing. So it need not to be go to the origin here. It can start it from origin or some distance, because it will be a threshold potential somewhere when the ions will start move, or ions will ionize, or the electron will emit from the tungsten filament. So that's how this graph we will get, and we consider this straight line curve. Only we calculate values in this range, because here the saturation will come definitely, because once all the ions will be ionized, then current will be constant value will be get, that is saturation. So we measure the values in this range pressure. Okay, so I hope you get the idea. So this is done for the day. Next will be the last for the error analysis, in which we will study the curve fitting. Okay, thank you then.